We will be digging into the details of that. So this is the outline of today's session. I will introduce what DAS is all about, and then go through the algorithm. We will go open one layer at a time so we can get some appreciation of the inner working of it. Then finally, we discuss why DAS is not widely used anymore because of its weakness, and we discussed this a little bit. So first of all, DES or DAS stands for Data Encryption Standard, and it is, as seen here, it is a block cipher, as explained last time. And these things I already explained. It was developed, it is a 64-bit cipher, which means it encrypts and decrypts 64 bits at a time. It was developed by IBM and the NSA in the 1977, I think. And then it was standardized in 1977 by NIST, National Institute of Standards and Technology. I remember this organization is behind a lot of cryptography systems, because for cryptography to work, the algorithm needs to be standardized. So all people, developers, and the hardware and software developers, they all implement it in the same way. Otherwise, you cannot be able to encrypt using one system and then decrypt using another one. So the algorithm is standardized. It was the most popular, the most widely used cipher until 2000, and then it was replaced by triple DAS and AES. Now, the golden standard for encryption these days is AES. Now, the length of the key, although the length of the key is 64, effectively only 56 bits get used. And I will explain how this really works. Now, this slide is very important. As we will see as we move forward and deeper into the ciphers, modern ciphers, they use these two primitive operations. These primitive operations are critical for modern ciphers. And these operations have been suggested by Claude Shannon. This is a very well-known scholar in communication, but he did some work also in cryptography. And he came up with these two fundamental primitives that are used by all ciphers. The first primitive, or the first fundamental operation, is confusion. In this context, what confusion means, we do some transformation to the ciphertext and the key in a way that there is no way to establish a relationship, any relationship, between the key and the ciphertext. So what I mean here, and this is commonly achieved through substitution. By the way, these concepts might kind of seem vague and high level, but we will see concretely how they are implemented in real ciphers. So confusion, we use substitution as a mechanism to hide the relationship, to hide completely the relationship between the key and the ciphertext. So if somebody, it is impossible to establish any mathematical relationship between the two. And this really translates into, if we do small change in the key, it will result in a major change of the ciphertext. So small change in the key results in a large change in the ciphertext. Now, the other operation is called diffusion. So diffusion means we are spreading, taking the influence of plain text, one plain text character, and spreading its influence to many ciphertext symbols. And basically diffusion is achieved by permutation. Now, to put this in a simple terms, ciphers or algorithms for encryption, they basically use a combination of substitution and permutation. Those are the ingredients of the magic that cryptography uses. In substitution, why do we use substitution? To create confusion. And why do we use permutation? To create diffusion. So not only this, we have to use both. We have to use both, and we have to repeat this multiple times. So these principles, we will see them as we start digging into the details of these ciphers. So to summarize, modern ciphers, they all use diffusion followed by confusion, followed by diffusion, confusion, and they use this in multiple rounds. For example, DAS, the data encryption standard, it uses 16 rounds of permutation and substitution. Permutation, substitution, 16 times. And the reason why we do this, you see this, it's to create this diffusion. So here's an example of what diffusion really means. Have a look at this plain text message, X1. And this is the ciphertext for this message. Yeah? Now, have a look at this X2. What is the difference between X1 and X2? Only one bit flip. One bit was flipped. Now, take a look at, after encryption through the block cipher, take a look at Y2. How many bit flips in Y2? 5. What this means, one small change in the plain text resulted in many changes in the ciphertext, which means the ciphertext, so the plain text, the relationship between the plain text and the ciphertext cannot be established. It's so kind of diffused and so spread into the ciphertext, you cannot work out any relationship between the two. Because here, small change resulted in big change that there is no way to undo it without, of course, without knowing the key. So that's what means by the result of this confusion, diffusion multiple times. The result is that one small change in the plain text results in many changes in the ciphertext. So to summarize, these are very important principles to keep them in mind. Kind of philosophical principles, but we will see how they are implemented in modern ciphers. Now, confusion, we already seen this, even in the Caesar cipher. If you look carefully, Caesar cipher, what it's doing really is just using substitution, which means it's confusing this hacker. They cannot work out what's going on. So, for example, in the Caesar cipher, we replaced with K3, we replaced A with D and B with E and so on. So using substitution, the result of substitution is that you cannot work out the relationship between the key and the ciphertext. Now, confusion alone is not enough, and we know this. In fact, your homework 1, you will break a couple of ciphers because they only use confusion. All the classical ones, like substitution cipher and the Caesar cipher, they use confusion. The modern ciphers, they also use confusion, which is nothing but substitution. But they do it in a much more sophisticated way, as I will explain in the case of DAS. Now, the substitution alone, history told us the cipher that uses only substitution can be broken. Now, diffusion, which is just using bit permutation, which is nothing but rearranging, like, for example, RC4. Remember, RC4 is just rearranging the elements. Those also can be broken. So if we just use substitution by itself or permutation by itself is not enough. What we have to do, combine both. Not only combine both, alternate both multiple times. And that's why this is the philosopher that came up with this great idea. And then modern ciphers, they all follow this idea of combining confusion and diffusion and repeating it multiple times. And this process is called product ciphers. When you hear product cipher, means For example, DAS is a product cipher. Why? Because it combines these two basic operations and repeats them multiple times. So this is conceptually the principles behind any modern cipher. So let's now start digging into the DAS and see how it uses these basic principles to come up with a very strong cipher. By the way, DAS or DES was never broken mathematically. There is no way to break it mathematically. It's only broken by brute force because it uses a relatively short key, 2 to the power of 56. Looping through 1 to the power of 56 is feasible with today's technology. Otherwise, it is still very strong, and that's why some people still use it, but they use triple DAS, which is doing the encryption 3 times using 3 keys. Then it's unbreakable. So now let's start opening the box of DAS and starting to see how the magic really works. In here, we'll go slowly, open one layer at a time so we don't get confused. So let's start with the high-level view. So here is the high-level view. So basically what we have here so DAS is a block cipher. It's the algorithm. It takes as an input 64-bit plain text. And then it takes a key. What is the length of the key? 56 bits. Although when you feed the key, you feed 64, but 8 bits will be ignored. The remaining 56 will be used. And then what gets produced after for each block, what gets produced? The cipher of that block. So because it's block by block, it takes in 64, it takes in a key of 56 and produces a block of cipher text, which is also 64 bits. Okay, now inside this black box, this is what happens. The first thing, we take the input and we do initial permutation. What is this initial permutation? What is a permutation in general? Rearranging. Rearranging the bits of this 64 bits coming in. We rearrange them in a certain way. In here, I will explain, as I said, in high level, and then we open every box and see what's going inside. Now, once we do the initial permutation, we go through 16 rounds of confusion and diffusion. 16 rounds of permutation and substitution, okay? And every round, we use a sub-key. So we enter or we feed in one key, and then based on this one key, we generate how many sub-keys? 16 sub-keys. So, and you will see this in all modern ciphers. They work somewhat similar idea. And then every box, of course, we will see how the 16 keys are generated from one single key. Okay, now once we finish with the 16 rounds, we do another final permutation. This final permutation, what it does, it will undo this initial permutation. Again, the details will be coming. So that's in high level how DAS really works. Okay. Now let us go inside one encryption round. One encryption round, how it looks like. Okay. So, as I explained, we have a key generation. This we will delay discussing it later. So for now, all you need to keep in mind, we have the initial key coming in as 56 bits. We do some transformation to this key and generate 16 subkeys. We will see the details of how to do that. Then, so the first step we do initial permutation. This is the plain text coming in, 64. We do initial permutation. And then we start our 16 round, one at a time. So the first step we do, we take the 64 bits And what we do to it, we chop it to half. So this one is the left half, and this is the right half. What is the size of each one? 32-bit, 32-bit, okay? Now, the right side, can you see the right side? All we do, we take it, we copy it to the left side, as it is. So the right side is not encrypted in the first round. Then the left side is the one we will encrypt. What's the operation used for encryption? XOR. We XOR it with what? With the output of this function. Now this is another black box. We will see what's inside. So what this F function takes as an input? It takes the right side and it takes the subkey 1. Yeah? So let me say it one more time. So here's my plain text coming in. What's the size of the plain text? 64 bits. What do we do with this 64 bits? Divide it into half. The right half, this is the input. So each round has an input and an output. 64 bits input, 64 bits output. Now, we take the input, we chop it into half. What we do with the right half, the right side? We just copy it to the left side as it is. Did it go through any encryption? No. The left side, before we copy it to the right side of the output, we go ahead and encrypt it. What's the operation, the encryption operation? XOR. We XOR it with what? We XOR it with the result of a function f. This function f, what does it take as an input? Two things. The subkey coming from the key generator and the right side. Yes? Okay. This structure, just for your information, this structure of doing things this way was invented by this cryptograph called Feistel. And this network, it's called Feistel Network. And this network is followed by many other algorithms, not only DAS. Okay? So the advantage of doing this, remember, if we just want to encrypt, it's simple. We can do the way we want and we can really confuse and diffuse the message. But what is the challenge? Is to do it. It's anything we do, we should be able to reverse it during the decryption. So the power of this Feistel cipher is that we can decrypt using exactly the same algorithm, zero change. The same structure, we use it for decryption. What gets changed when we decrypt? The only thing that changed is the keys. So first time we have key 1, 2, 3, up to key 16. In the decryption, we'll have key 16, 15, up to 1. The rest, the core of the algorithm, exactly the same, zero change. This is the power of this Feistel cipher, Feistel network. It is not a cipher or an algorithm on itself. It is an approach that many other algorithms follow. And the approach is very simple. All you do, you take your cipher, you chop it into half, 32 bits of each, the left half and the right half, and then the right half, you just copy it to the output of the left half of the output, and the left half, you encrypt it using the output of a function, and this function takes as an input the subkey and the right half. Yeah? Now, this is like visually how it looks like. Mathematically, this is how it looks like. Have a look. Mathematically, what we do is the output is basically the left output is the right input of the previous round. You see here, the left output is basically the right input of the previous round. Yeah. So basically, what we have here, Li is equal Ri minus 1. Yeah. What about Ri? Is the previous left, we XOR it with a function that takes as an input the previous write and the subkey of the current round. Yeah, so this is like visually, but really inside it's really everything is mathematically expressed. So I hope it's clear, the idea. Okay, so now what is left here is opening these boxes. We need to know what do we do with this inside this initial permutation, what do we do in F, and then what do we do for the key generation. Yeah, but you need to go like one layer at a time so you get the idea. Okay. Of course, we do this 16 times. In the last round is exactly the same. And after the last round, what we do final permutation. Remember, we started with an initial permutation. We went through 16 rounds, and then we do final permutation, and that will be your ciphertext for that particular block. And you do this if you have a big message. You do this for each 64 block. You keep doing this. Okay, so now let's go one layer down and have and open these boxes and see what's inside each one. So what was the first step of the DAS encryption algorithm? Initial permutation. Now what is permutation? Rearranging. Do we just, in this scenario, do we just rearrange in a random way? If we do that, of course, we will have an encrypted message. Nobody can really know what it is, but we cannot decrypt. So what do you think? How we will do the permutation? So we do the permutation according to some tables already provided by DAS. The people who designed this algorithm, they provided these tables. So how we use these tables? Very super simple. So we said how many bits we are taking as an input, 64 bits. So we put them like, let's say, an array. The first element is 1, the last element is 64. So each cell has a number, 1, 2, 64. And all we do, we follow this table. Although this table is supposed to be stretching as one line, we just represent it here in 8 columns and 8 rows. But really, in reality, it is, you should imagine it as one long array. So all we do is, this is the input and this is the output. Yep. Now, the inputs are arranged from 1 to 64. The output should be arranged this way. The first bit should be the 58 bit. Here is 58. We take the value here. It could be 0 or 1, and we copy it to be the first element. What will be the second element of the output block? 50. We look at 50. We take 50 and we copy it over. The third element, 42, and so on. The last element, 7. We take element 7 and we copy it over, and this will be our permuted block. So this is straightforward. We just follow this table that they gave us. At the end, after the 16th round, what we do? We do another permutation, and this time we use this. This is the initial permutation table, and this one is the final permutation table. It's known as IP to the power of -1. So in here, this one will be the ciphertext. What we do is you permute it, we rearrange it. How we rearrange it? The first element element 40 becomes the first, element 8 becomes the second, and so on. And the last element, 25, will become the last element here. That's what permutation means. We do it according to these two tables provided by DAS. You might be thinking, this is the magic behind the encryption. It's like the other magicians, they use, I don't know, they say some weird saying, they make uqad, and they do some other, they say some weird words. And here also you find a little bit of weirdness, but behind it really is a complex mathematical stuff. Yeah, yes,
Why do you
please.
have to do the initial computation if the new order is already written in?
This one really very hard for me to answer, but according to my research, this initial and final permutation are mainly there to make it easy for wiring because this algorithm was initially implemented using hardware. Okay. Now, what this means, why it's really done, I cannot answer, unfortunately. But according to my reading, it's mainly to make it easy for implementation. So this does not affect security. This initial and final permutation are mainly there to help with the hardware-based implementation. That's according to my research, because I was always also puzzled. So far, this is not the secret sauce that makes the encryption. I will highlight it as we move forward. But here, if you want to implement DAS, you have to follow this. This is the standard. These tables, you can find them in this Wikipedia. Anyone who wants to implement this must follow this. Yeah? It's like one of those things. مفعول به مرفوع, مفعول به منصوب, مفعول به منصوب. That's it. You cannot come and change it. No, I don't want to have 58 there. I want to have 56. No, you cannot do it. It's a standard. Standard means, خلاص, you just close your eyes and follow it. Otherwise, you will be implementing something other than DAS. DAS, this is the tables that comes with DAS. Which means this algorithm, when it first came out, people were very suspicious that behind these tables, this is not the only tables, you will see more tables. People think, oh, because NSA is behind this, National Security Agency, they thought there is some backdoor, some mathematical backdoor, they can break the encryption by themselves or some other, or they have some tricks behind the scene. But apparently, a crypto analyst, they analyzed this algorithm so deeply, and no trick and no backdoor in this algorithm. It's very secure, very, very secure. As I mentioned, the only way to break it is through brute force. Yeah. Okay. And as I explained before, DAS is the most deeply studied crypto, in terms of crypto analysis, the most deeply studied algorithm. Because there was a lot of conspiracies. This was the first standardized algorithm, Cipher. And it was widely used, so a lot of researchers digged into it to try to break it, and they couldn't break it. Mathematically, I mean. Okay, so initial and final permutation, is it clear? Yeah. So what I found, I should have kept the resource. I found one Excel spreadsheet somebody has developed that shows this one step at a time. So let me just show you, just each step. Once I explain this, I'll show you in this Excel spreadsheet, and I will post this one online. So here is the 64-bit. This is the original message. Here you just need to understand the idea. Like the encryption will no longer, after this session, is no longer magic. It's a set of set of steps and algorithms you go through to produce a ciphertext. Okay, so here is the original message. It has 64 bits, so it goes from 1 to 64. Yeah, this is the initial arrangement of the original text. And this is the permuted text. All you do, go to the DAS table that the DAS designers produced, and you put the bit numbers that they have provided. The first bit should be 58, the second is 50, and so on. You put them there, and you go and do a lookup here. So 58, where is it? Bit 58? Here is bit 58, which is 0. Take 0 and copy it here. Yep. Now, where is bit 50? 50 is here, 0, take it and copy it there, and so on. And then you will get, at the end of this operation, you will get your permuted 64 bits. Now, once you do this, next step is to do the encryption round. Remember the encryption round that we discussed? Now, the encryption round, I already explained it. What is not clear in this diagram? What is the black box? We don't know how it works. The function. The rest is understood. So now let's dig into this function. This F is really the heart of the algorithm. Now, first of all, let me ask you one question. Which part gets encrypted? Is it the left side or the right side in every round? The left side. The right side is not encrypted. It is copied as it is to the right side. Sorry, to the left side. So the right side does not undergo any encryption. You see here the line? Just copied as it is. What undergoes encryption is the left side. We encrypt it and we write it to the right side. Now let's open the F box and see what's in there. So the F box has four steps or 4 operations. The first one is expansion. Remember, the right side, remember the F, what is the input of F? The sub key and the right side. What is the size of the right side? 32 bits. What is the size of the key? 48 bits. So the key is 48 and the right side of the block is 32. We cannot do an XOR with 32 with 48. So what should we do with 48? We expand it. So the first step is we take the 32 bits and we expand it to 48 bits. How do we do the expansion? No, not padding in this scenario. We use another table. So the DAS designers, they gave us another table that transforms, like in this case, it transforms each bit. It's basically a permutation table. It does permutation and at the same time it expands. I will show it to you shortly. But the first step is expansion. The next step is XOR. This is super easy. We expand the 32 bits into 48. We take 48 coming as a subkey and we do XOR. Then we go ahead and do substitution. So we have 48 bits, yes? Now if we divide 48 bits by 6, 48 divided by 6 is 8. 8 times 6 is 48, yes? Okay, now, so what we do is we take six bits at a time, and we substitute them with 4 bits. So we take 6 bits and we substitute them with 4. Again, how do we do this substitution? Yet another table. How many substitution tables we have? 8 substitution tables. 8 substitution tables. What do we call these substitution tables? S box. S box. These S boxes, the magical S boxes, are the heart. The whole trick of the whole algorithm is this S box. Then finally, we do permutation, and that's it. You will get the output of F. Remember the output of F? You will get it. So you can see, remember we started that the basic operations of any modern ciphers is we have substitution to do confusion, and we have permutation to do diffusion. You can see here it is done multiple times, and we repeat this how many times? 16 times. Okay, so let us now dig into each step very quickly. Expansion. First, let's look at the expansion. So the expansion, what we get as an input, 32 bits. What we produce as output, 48. Yes. How do we do this? All we do, we take our 32 bits. So we put it's kind of an array. The first index is 1, 2, 3, 4 until 32. Yes. Then we produce 48 bits. How do we produce these 48 bits? Using this E table. So what this E table says, okay, the first bit of the output will be 32. We go to 32, we copy it in the first one. Yes? Now the second bit should be 1. Can you see it here? Becomes your second bit. The third bit should be 3. 3, copy it over. And so on. But in here, how many bits we have here? 48. So what does that mean? Some bits will be repeated. Thank you very much. How many bits will be repeated? We have 32 and we have to produce 48. 16 need to be repeated. One of them, if you can notice here, one, you see here one, is repeated twice. It's copied in one is copied to the second position. Can you see it? And also one is copied to the last position. That's all. This is the magic. This table, they came up with this table. They gave us this. Of course, these tables behind them a lot of magic in a way that you can undo the encryption, but you cannot break it. Okay, it's clear what the expansion is doing? Very simple. It's taking 32 bits, expanding it to 48. How does it do so? Using this E table. That's all it does. Okay, now the next step is XORing. This is simple. All we do, the output we get here, we do XOR with what? The subkey that's coming. 48 bits subkey, we XOR it with the result of the expansion. Now, once we do this, it's time to do now the S box, the substitution. This is the heart of the algorithm. This is what makes it unbreakable. Now, what we do, we take the 48 bits. What do we do with the 48 bits?
Divide by 6.
We chop them into 8 sub-blocks. Each sub-block will have how many bits? 6 bits. Yes? 6 bits. That's what this is trying to illustrate. So every 6 bits become, the first 6 bits is S1, S2, S3, up to S8. So basically, 8 times 6 is 48. Now, for every 6 bits, we replace them with a 4 bits. Yeah? How do we do this? How do we do the substitution of 6 bits with 4 bits? You use yet another set of tables. This time, what we call these tables? S-box tables. How many of them we have? 8. Now, the magic trick is how do we use these S-tables? How do we use these S-tables? Okay, so in every S, how many bits we have in every S? 6. So the tables, these S-tables, this is how they look like. This is one of them. Yeah, you can find these tables if you do S-blocks on Google, you will find them in Wikipedia, in many places. Now, how do we look them up? These tables, how many rows they have? 4 rows, from 0 to 3. And how many columns? 16 columns, from 0 to 15. So all we do, we take these 6 bits. This is an example. 6 bits is, in this case, 100101. Yeah? Now, what we do, we take the leftmost and the rightmost. What are the leftmost and the rightmost in this case? 1, 1. 1, 1 in decimal is 3. 1, 2, 3. Yes? The CE people, you agree? Yes. 3. Okay, what do we do with these 3? This is the row. We found the row. Now it's time to find the column. How do we find the column? The middle 4 bits. The middle 4 bits. Yes? So what do we do here? What's this number? 2. This is basically 0 and this is 2. Yep. So 2. Here is 2. So I intersect column 2. Sorry, column 2 with row 4. Row 3. Yes. Sorry. Yes. Basically, the value here is 2 plus 3 is 0.8. Yes, is it clear? So basically, I keep doing this for all these guys, using these S box tables. Yeah? Now, of course, you need to memorize all of these boxes. Let's go. Yes, and then of course, once you find the 08, you will represent it in binary.
Because the 0 will be 4 digits, sorry, 4 bits, and the 8 will be stored. How do I have 8 bits? Originally there were 6.
No, they will be 6. It will produce 4 bits. All these can be represented as 4 bits, all these numbers. So we take in, so basically the S boxes, what they take in? 6 bits. What they produce? 4 bits. So this, for example, what was the intersection here? This is the row. Third column. This is the third column, which is 2, and the fourth row, which is basically 08. 08, you represent it in binary, and that's your output. Yes? Now, once you produce this, you look up every, by the way, S1 has its own table, S box 1, S2, S box 2, and it works the same way. It has basically rows and columns. The rows, the way we work out the row, we take the leftmost bit and the rightmost bit, and basically we convert it to decimal. In this case, 3. Basically, this is the row 3. Now in here, we take the middle ones and we convert them to decimal. This happens to be 2, and basically this is our column 2. So the intersection between the second column and the third row gives us the value we will do the substitution with. So here is the input, and will be replaced with 08. Whatever was the input will be replaced by 08. And we do the same for every S. But every S has its own tables, its own table. So we have 8 S box tables. Okay, the last step is we do yet another permutation. Yes, please. Okay, from where we get these 08? These are the Das magicians, Saharat al-Das. So they gave us these tables, okay? And these tables are the magic of the encryption. These tables are done in a way the encryption can be undone, decrypted, but you cannot break it. Yeah? Yes, please.
Will you classify 08 like bitwise?
Yes, bitwise.
So it will be 001?
Yes. Is clear? Once we finish with the substitution, we do yet another permutation. Remember, why are we doing this? Substitution permutation, and we do it multiple times. This is the only way to get unbreakable cipher. You saw the principles we started from. You have to do a product cipher, which is an alternating between substitution and permutation, and doing it multiple times. The final permutation, what do you think? How the permutation will be done? Another table, thank you. That's it. This is the permutation. Very simple. How many bits we have now? 32. Remember, we started with 32, we expanded to 48, we did an XOR, then we come up with, we have an output of 48 bits. How did we arrive to 32 bits? Using substitution through the S box tables. Now we have back to 32 bits. Do we just push it to the next round, or before we give it to the next round, what do we do with it? We do permutation. How do we do permutation? According to this P table. Exactly the same idea. The 16 bits will become the first one. The 7th bit will become the second one, and so on. And you construct the permuted table. Okay, now, the last thing I want to show you is the key schedule. Remember the key? Every round has its own key. How many subkeys we produce? 16 subkeys. How do we produce them? This is the algorithm. This is the magic of the key. And by the way, if you understand DAS, you will be able to easily understand others. They use kind of similar. Of course, every magician has their own tricks, but they have some commonalities. So For example, AES, which is a very modern cryptography, came up only in the year 2000. Maybe it's younger than some of us. Even that one uses these magic tables. There is some substitution table to replace some plain text bits with some magical bits that the ES table will give you. Yeah. So substitution, as I said, and permutation are the basic building blocks. You will find it in all ciphers. Back to the keys. So what did we say? Each round, it takes a sub key. What is the size of the sub key of each round? 48. Yes. Now, what is the size of the key we give to DAS initially? What is the size? 64. Now, what is the effective bits that get used? 56. So what happens is the last bit of every byte. Remember, 64 bits is 8 bytes. So every 8 bits, the last bit is ignored. We throw it away. Okay? So to create keys, the first thing we do, these magicians, they like chopping things. What they do, they take the key, chop it in half. Each half will have how many bits? 28. Because we ignore we start with 64, we ignore 8. How many left with us? 56. What do we do with this 56? We chop them in half. One half of the key will have how many bits? 28. The other half will have 28. Yes? Now, the bits that will go to the left, yet another table. We call this table PC1, permitted choice 1. These are the bits of the left side of the key, and these are the bits of the right side of the key. Yes? So what's the size of the left side of the key? 28 bits. What's the size of the right side of the key? 28 bits. And here is how we generate the key. Please bear with me. Just give me 2 minutes. This is how I generate the key. I have 2 parts. What I do, I take the left part and shift it by 1. What I mean by shifting by 1, let me show you. Very simple one here. Here is my sub key, left side. What I mean shift by 1, I move all these guys, take this 0 here and put it to the end and shift everything to the left. Yep. And I do the same for B0. I shift to the left, which means all of them will shift and this 0 here will come to the end. That's what means shift. Okay, once I do this shift to the left, by the way, for round 1, 2, 9, 16, I shift by 1. For other round, I shift by 2. This is not my saying, this is DAS magicians, that's what they say. Once I shift each side of the key, left side and right side, I still have 56 bits. What I need to do, I need to produce out of this 56 bits, how many bits I need to produce? 48. How do I produce these 48 bits? Using yet another table, PC2. How do I produce it? I'll say 14. These are the lucky bits that will be used in the subkey. Yeah, 14, 17, 12. And then this will give you 48 bits. What do I do with this 48 bits? I give it to the round to use it for each round. For each round, how do we generate the next key? By shifting the bits. The left side, either by 1 or 2 bits. Shifting the right side, either by 1 or 2 bits, depending on the round count. And then once I get the 56 bits, I produce out of them 48. How do I produce the 48? Using PC2. And I keep repeating this, how many times? 16 times. By the way, if you look carefully, 4 rounds will shift by 1. Yes, 4 rounds will shift by 1. And 12 rounds will shift by 2. How many shifts I will have? 28. At the end of the day, the last right side of the key and the left side of the key will be equal to the initial keys. Why do you think this is important? For the decryption. So the decryption will start from the same original key, from the same one. And then the decryption will start. The decryption and encryption is exactly the same step. What is different? Key creation. It will produce key 16, key 15, and so on until to the key 1. It's only reversing the order of key creation. The rest of the algorithm is exactly the same. It will be using the substitution tables, the S boxes, all the steps exactly the same. The only difference is the key. And this is the magic of DAS. It's so impressive. I know there are a lot of things, a lot of steps, but you don't need to, you just need to understand the overall idea and the steps. So when you look at this ciphertext produced like Chinese from something that was meaningful, it is really magical. And this is what is inside this magic box. That's what this lecture tried to do. So I think this is enough. What I will do, I give you the Excel spreadsheets. If you have time, you can go through and just make this more meaningful to you. Next time, we will see how AES works in a similar fashion as DAS. Only these two algorithms, just as example for us to see how modern ciphers really work, the inner working of these modern ciphers.